Voltage divider bias method. Here, this is the most widely used method for providing biasing and stabilization of a transistor. In this method, we are using two resistors R1 and R2, which are connected across the supply voltage VCC. This is the VCC to provide necessary biasing. The emitter resistor RE provides the necessary stabilization also. This is RE. For stabilization, we require the necessary base emitter voltage. This base emitter voltage, for faithful amplification, the required base emitter voltage is supplied by the two resistors R1, R2 and the base emitter resistor RE. The voltage across R2 forward bias the base emitter junction. This causes proper base current and hence proper collector current to flow in the zero signal current. For faithful amplification, we know that the three required conditions are the zero signal collector current, zero signal base current and proper base emitter voltage. The forward bias voltage VBE across the base emitter junction is determined by the emitter resistor RE, this is RE, then R1 and R2. Now let us go through the circuit analysis. Consider the circuit here. This is the transistor. This is base, emitter and collector. Emitter is connected to a base emitter resistor RE and a capacitor CE is used to bypass the AC components. Okay. Then the two resistors R1 and R2 are connected across plus VCC. From plus VCC, R1 and R2 are connected to the ground, and RC is the resistor across the collector. This is RC is the collector current that is connected to plus VCC. Let us apply the Kirchhoff's law. Here total current I1 passes through R1. Here at this point it gets divided into two, IB and I1 minus IB. But IB is very small in the range of microamperes, hence we can neglect IB and therefore approximately I1 is flowing through R2 also. So applying the Kirchhoff's law, let us consider this portion. Okay, plus VCC is the supply voltage. The voltage is dropped across R1 and R2. So we can write plus VCC. VCC is equal to I1 R1 plus I1 minus IB into R2. So VCC is equal to I1 R1 plus I1 R2 itself. Since IB is very much small, we can neglect this IB and hence I1 into R2 can be written. So VCC is equal to I1 into R1 plus R2. Therefore, from that we can calculate I1 is equal to VCC divided by R1 plus R2. Therefore, the potential difference across R2, this is the base emitter voltage. Actually, base emitter voltage is VR2. VR2 is equal to I into R2. I is VCC by R1 plus R2. So, VR2 is equal to VCC by R1 plus R2 into R2. Let's have an analysis of this equation. This VR2 means it is the base emitter voltage. This is equal to VCC by R1 plus R2 into R2. That is VCC is a constant, R1, R2 are also constant. Hence, the base emitter voltage is independent of transistor parameters. That means it remains constant. Next, V2 means V2 can be represented as VB, base emitter voltage plus collector emitter voltage. That is VBE plus IERE. So we can write V2 is equal to VBE plus IERE. That is IE is equal to, from this IE is equal to V2 minus VBE by RE. But we know that IC is approximately equal to IE. So we can write IC is equal to V2 minus VBE by RE. First portion, that is the collector expression for collector current that we have already obtained. Next, the expression for collector emitter voltage. Collector emitter voltage VCC is equal to VCE plus ICRC plus IERE. Here, considering this mesh, okay, plus VCC, this is the supply voltage, this is dropped across, this is this resistance, that is RC into IC, and this is the collector emitter voltage, and this is the emitter voltage. Emitter voltage is I into RE. So total voltage VCC is equal to ICRC plus VCE plus IE into RE. Therefore, VCC is equal to VCE plus ICRC plus IC into RE, because IE is approximately equal to IC. From that, VCE is equal to, we taking VCE here alone, VCC minus ICRC minus ICRE. That is combining with this VC equal to VCC minus IC into RC plus RE. Next we have to consider the bias stability. Bias stability means how in the potential divider biasing, how stability is established. Here IC is equal to collector current is equal to V2 minus VB divided by RE. Since VB is very small compared to V2, we can write IC is equal to V2 by RE. But we know that V2 is equal to VCC by R1 plus R2 divided by RE into R2. This shows that IC is, that means here VCC constant, R1, R2 are constant, RE also constant. That means IC is independent of any other parameters. It depends only on R1, R2 and RE and source voltage VCC. So there is stabilization of Q point against the individual variation. Individual variation means the variation due to temperature and variation due to thermal runaway. Stabilization is obtained for temperature variation also. As temperature increases, then how temperature variation? You know that as temperature increases, the current collector current also increases and thereby changing and thereby causing instability. But in potential divider arrangement, what happens is that as temperature increases, the collector current increases. So as collector current increases, what happens is that emitter current also increases. So an increase in IE causes the voltage drop IE-RE to increase. So what happens is that the base emitter voltage V2 is equal to VBE plus IE-RE. As IE-RE increases, what happens is that VBE decreases since V2 is a constant. As already we said that V2 is equal to VCC into R1 R2 by R1 plus R2. That is, it depends on R1 R2 and VCC. That means V2 is a constant. As IE increases, IE-RE increases, hence VBE must reduce to make it constant. So a decrease in input voltage VBE causes decrease in input current IB. The decrease in IB tries to restore the collector current to its original value. Hence stability is attained. Then stability factor. Stability factor, the equation. We don't want to derive the stability factor equation. Just we just know the equation only. S is equal to beta plus 1 into within bracket RE plus R1 R2 divided by R1 plus R2, the whole divided by beta plus 1 RE plus R1 R2 divided by R1 plus R2. If RE is very much greater than R1 R2 divided by R1 plus R2, we can neglect R1 plus R, we can neglect this quantity. So what will happen is beta plus 1 into RE divided by beta plus 1 into RE. That is, stability tends to be 1. That is, it is the maximum attainable stability, and this is the most stabilized biasing circuit.